Okay. Good afternoon, everyone. Welcome to this live session on 8th December 2025. So, in this live session, what we'll do is we'll continue the uh, uh, this will be the continuation from the previous week that we'll be discussing this state space analysis, and the mostly will concentrate on the consider this is as a problem solving session. So if you're having any doubts in the previous live session, you can ask me for 5 minutes, because those topics are also I mean, we'll be using those topics here for solving these problems. If you have any doubts, you can ask me. So, or else while solving the problems, we'll be reviewing those topics. That time also you can ask the questions. Okay. So let's see the problems. So look at this first problem. Hope you can able to read the problem. Okay. So we have this single input single output system. Okay, so we have a single input single output system that represented in the state space representation. We know we can represent the state general state space system as ax plus bu and y is equal to cx plus du, where a b c d are the matrices. Correct. So x is the state, u is the input. Okay. So that we know already. Suppose here the question is that we change the existing state to the new state. So that means new state is here, the existing state is x. So this is existing state. So we are changing that one to new state as zeta. So existing state is xi. We are changing to new state as zeta I, which is nothing but ki xi, where I varies from 1 to n. Okay. So we are transforming the state from xi to zeta I. Then the question is, the first question is, so express the matrices in the zeta coordinates. So zeta coordinates, what are these matrices becomes? So with the xi x coordinates, the matrices are A, B, C, D. So when we do the transformation, what are these matrices would become? That is first question. Second question is, suppose if we introduce a scaling in the scaling tau is equal to gamma t. Okay, so new time scaling. Okay, again, so how these matrices would change? So matrices of A, B, and C, D, how do they change? This is our question. Okay, I hope the question is clear. So our initial system is given to us as a single input single output system. So we know that we would be representing, we could represent them using these two equations. X dot is equal to ax plus bu. Then state has been transformed to a new state zeta I. So with this relation, zeta I is equal to ki xi. Then find the matrices in the zeta coordinates and find the matrices when there is a scaling in the time. Okay. So let's solve this problem. Okay, so now we have from the this equation zeta I equal to ki xi. Okay, so where I varies from 1 to n. Okay, so that means this equation does looks like, so zeta 1 is equal to k1 x1. So zeta 2 is equal to k2 x2, etc. You'll have zeta n is equal to kn xn. Okay, so this we can write it is as zeta 1 zeta 2 in the matrix form, zeta n equivalent to 2. So this k matrix multiplied by the x vector. Okay, so this is zeta, k, and x. where so we have to write the matrix form in such a way that these equations get satisfied. So that means we can write it like this: k1 k2 in their diagonal form, okay, and here x1 x2 etc xn, okay. So here all these terms would become 0, these terms are become 0. So that means your k matrix is a diagonal matrix, okay. So either we can call k or t matrix. I hope this is clear, okay. So now we can write it like, let's call this is t instead of k, so that we don't get confused. So let's call this is t, okay. So that means now zeta is equal to tx. This is what the relation we have, okay. Okay, now we have zeta is equal to tx, so we can write x equal to, so 1 by t zeta. So let's call this one as x equal to some matrix v zeta, okay. So matrix v zeta, where again the v is nothing but what, so here v is 1 by tau, which is nothing but the tau inverse, okay. So that will be 1 by k1, 1 by k2 etc, 1 by kn. This is the matrix, so all these terms are zeros, okay. So that is our new matrix V. Now let us look at the question. So the first question says that we need to have those, the question 1, question A. So we already have this ax equal to bu and y equal to cx plus du, correct. So in this, okay, in this, so what do we have from this equation? X equal to v zeta, okay. So but here if we are looking for x dot, okay, x dot equal to what, v zeta dot, because v is a constant matrix. So from here how can we write, so from this equation how can we write x dot equal to, sorry, so v zeta dot equivalent to 2, okay. So v zeta dot equivalent to 2. So how can we write, so just a minute. So we have here, so x dot is equivalent to v zeta dot, okay. So that we can write it like a multiplied, what is x here, v zeta, okay. So we are writing from this equation only, we are writing from this equation only. So v zeta plus bu, okay. So this implies here, so from here we can write zeta dot as, okay, zeta dot as v inverse a v, because this v goes that side, multiplied zeta plus bu, okay. So I think it is clear. Next we have second equation, y is equal to cx plus du. See what is x here, x is nothing but v zeta plus du, okay. So that means y, what do we have, y equal to cv zeta plus du, okay. Now you look at the two equations. So this is our first equation, this is our second equation, okay. So from this these two equation, what do we have, so that is, that represents the that represents the state equations in zeta dot. So what is that equation, two equations I'm writing again. So that is, first one is v inverse av zeta plus v inverse b, okay. So here this v inverse should be there, v inverse bu, v inverse bu. Second equation is y is equal to cv zeta plus du, Okay, so now you can see we started with x dot is equal to ax plus bu and y is equal to cx plus du. Okay, and we know the relationship as zeta is equal to tx. Using these two, so we got our new state equations as these two. Okay, so here we can write this one as, so zeta dot equivalent to 2. So we can write first term as a zeta zeta plus, so b zeta u. Second equation as c zeta zeta plus d zeta u. Okay, so where a zeta is nothing but v inverse a v. Okay, so now we already know the expression for v. Okay, so v is nothing but this matrix. Okay, v is nothing but this matrix. So let's write down that. Okay, so 1 by k1 etc 1 by kn, these are all zeros. Inverse, so let's choose some a matrix as a11 etc a1n. Similarly an1 etc ann. Okay, and last matrix is 1 by k1 etc 1 by kn. These are zeros. Okay, so now if you see here, so we know how to calculate this. We can easily do the calculations. Okay, so to find the a zeta, here calculations are not important, just to we'll check what is this. Okay, next similarly we can also find b zeta, which is nothing but v inverse b. Okay, so that is nothing but 1 by k1 etc 1 by kn. Okay, 0 0 inverse, so this is going to be b1 etc b n. Okay, so you will get what, b1 k1 b2 k2 etc bn kn you'll get. So this is the expression for uh, b zeta. Similarly we can also find the c zeta as cv. Here you could see c zeta as cv. Okay, so c is nothing but c1 c2 etc cn. So 1 by k1 etc 1 by kn, these are zeros. So you'll get what, so c1 by k1 etc cn by kn you'll get here. Okay, so finally d zeta is d only. Okay, so these are the four matrices. These are the four matrices. So first we have started with these state space equations. Then we got the, using this transformation, we got the state space equations in the new variables zeta and y. Okay, so these are the dynamics. Then initial matrices are A, B, C, D. Then new matrices are A zeta, B zeta, C zeta and D zeta. This is our first question. Okay. Is there any doubt in this? Any doubt or query in this? So here we saw how we have transformed the matrices to the new state variables. Okay. So that is our first question. Second question is, let's go back and see the second question. So second question is, suppose now we are introducing a time scale of tau is equal to gamma t. So when we introduce this, what will happen to the matrices again? Okay, so we need to some hint is given. So dx by d tau, dx by d tau as dx by dt, dt by d tau. Okay, so what is given? So a new time scale is given. So a new time scale of tau is equal to gamma t. So from here we could write t is equal to tau by gamma. Okay. So what is our goal here? Okay, so the goal is to express system, okay, given system in uh, uh, system in tau and zeta, okay, tau and zeta. So these are the two things. So tau and zeta systems in terms of A, B, C, D, and Ki and gamma. Okay, so starting continuation from the previous one. Okay, so now here we have x dot is equal to a hint also given to us. So the hint says that, okay, so dx by d tau equal to, so dx by dt multiplied dt by d tau. Okay, so this with this new time scale, so what would happen to the matrices again? So we have to use this hint. That is the question. Okay, so let's write down them again. So x dot is equal to ax plus, so bu y is equal to cx plus du. Okay, so here x dot is nothing but what? Dx by dt. Y is y of t. This is dx of t by dt. Okay, so now what is our question? When we transform, what do we get? We are transforming x and y into zeta and y. So then it would become like d zeta by dt of t, which is nothing but zeta dot. Okay, which is nothing but a, let us call a new matrix as a tilde zeta, okay, plus b tilde u, okay, b tilde u. Similarly, y as, we can write matrix y matrix as c tilde zeta plus d tilde u. Okay, so these are the two things we have. We have to find the new system where the time scaling is given as uh, t equal to scaling by a factor of tau by gamma. Okay, so this is what given to us. So our job is to find, we need to find this. We need to find this. We need to find this means what? We need to find the a tilde, b tilde, c tilde, and d tilde. Okay, so let's write first thing as zeta dot. Zeta dot is nothing but what? D by dt. Okay, so tau by gamma. Okay, tau by gamma. So this we can put it like, so d by d tau. Okay, so this is what the zeta is, because here zeta is nothing but, so this is zeta of, I'm sorry, the question being asked, this is zeta of tau by gamma, this one, because that is the time now. Okay, let me write it clearly. Okay, so this will be tau by gamma. In place of t, we need to get tau by gamma. Here also, so tau by gamma. Okay, so now this is what we are looking for. Okay, so then here we can write this one as, so d zeta by d tau, tau by gamma multiplied d tau by dt. Okay, so this is this we can write it as, because you are doing with respect to the tau. Okay, so d zeta d tau by gamma. Okay, d tau here, so this will be gamma. Okay, because tau is equal to, from here tau is equal to t gamma. Okay, T gamma because you are doing with respect to the T. Okay. So from here we can write, so d zeta by d zeta of tau by gamma by d tau is equivalent to what? So this gamma you are bringing this side all the way. So 1 by gamma, so this zeta dot. Okay. So now 1 by gamma, what is this zeta dot is? So zeta dot from the previous problem we have V inverse AV zeta plus V inverse BTU. Okay, so we have already seen this as A zeta and this as B zeta. A zeta and B zeta. Okay, now we can write this one as, so 1 by zeta A zeta, okay, zeta of tau by gamma, okay, plus 1 by zeta B zeta, okay, again u also in terms of tau and gamma, because u of t, here t is nothing but tau by gamma. Okay, so this is what the uh, first equation is. Okay, so this represents what? Zeta dot. Okay, so this is the final expression. Okay, next similarly we could write, okay, so y of tau by gamma, y of tau by gamma, so that is nothing but c zeta, c zeta, okay, so zeta of tau by gamma plus d zeta u of tau by gamma. So this is second equation. This is second equation. Now you could see here both these equations. Okay. So from both the equations, you can say, I'll write with another color. Okay. So this part, okay. So that is first part. So this is second part and third part, fourth part. These are the four matrices. Okay. So when you take the time scaling, what is happening to the matrices? So the matrices are becoming, so multiplied with 1 by zeta here, 1 by zeta here, and C matrix and D matrices are stay as same. Okay, so that's how the new matrices change. So overall, what is this problem we are doing in this problem? So first one is, so let me give you the overview. So first we have this x dot is equal to ax plus bu, y is equal to cx plus du. So this state space equation system is given to us. Okay, when here the state is xi. Okay, when the state is transformed, okay, by multiplying with some constant, what happened to the ABCD matrices? That is the first question. Okay, second question is, when we do the time scaling, what happened to the matrices from the previous question? Okay, so when we converted the system from xi coordinates to zeta coordinates, what happened to the matrices? So the matrices has changed like this. They are changed from A, B, C, D to this matrix, which we have called as A zeta. This is BZ, CZ, and DC. Then after introducing the time scaling, so matrices, previous matrices, time scaling of zeta here. Okay. Then matrices were factored by zeta. Okay. So matrices were so multiplied with 1 by zeta. This is the flow. Okay. Any query in this problem? Any question or doubt?
No, sir.
Okay. Yeah. So you can check these calculations once again. Okay. Yeah. Next question. So I think in the previous class, previous week, we have this finding the equilibrium points. Okay, and then linearizing the system about that equilibrium point. Okay, so let's solve one more question quickly. Okay, so basically equilibrium point means, so it is the point where the system states will not change. So that means usually when you have a state of the system as x, so at equilibrium, so the change in the state would become 0. Okay, so that is called as the equilibrium point. So generally for any system, when it is non-linear, so they have system format in this way. Okay, so x dot is equal to f of x comma u, so y is equal to z of x comma v. So this is non-linear. Okay, so non-linear system. So when you do the linearization, so about equilibrium point, so you will write the above nonlinear system as this equation: x dot is equal to x plus bu, y is equal to cx plus du. Is that clear? So at this equilibrium point, system becomes linear, or we call it is as a linearized system with respect to this equilibrium point. Is this clear? Any doubt about equilibrium points? Any conceptual doubt? Okay, so so the equilibrium points, usually here we have four equations: x1 dot, x2 dot, x3 dot, and y. Okay, so at equilibrium, so you will have x1 dot equal to 0, you will have x2 dot equal to 0, you will have x3 dot equal to 0. Okay, and along with these, you will also have all inputs also 0, all inputs also 0. Okay, equilibrium, all the inputs becomes 0. Okay, so now in this case, this is at equilibrium, conditions for equilibrium. Okay, so now let us consider one by one. Okay, so let us consider this one as first equation as, okay, so f1 of x comma u, second equation as f2 of x comma u. Okay, third equation as f3 of x comma u. So let's say fourth equation is, let's say g of x comma u. Okay, so now as I said, at equilibrium, all these derivatives would become 0. So when x1 dot equal to 0, so that means what? Minus x1, x2 plus 1 equal to 0. Okay, so what does this becomes? X1 is equal to 1 by x2. Okay, next, second case, when x2 dot equal to 0, what do we have? So also you need to take u1 comma u2 also 0. That is the condition for the equilibrium. So now the second equation becomes minus, sorry, so this would become x1 x3 minus x2 plus u1 plus u2 square 0. Here the inputs must be 0. Okay, so what do we get in that case? So we will be getting x1 x3 equal to x2. So this is second condition. Okay, next third one, third equation. Okay, so third equation is so x3 dot equal to 0. So what is x3 here? So x1 square plus x2 plus x3 plus u1. Okay, so this u1 is already 0 because we are checking that the equilibrium condition. So what do we get here? So we get the third one. I'm sorry, this is the fourth one. Yeah, not this. X3 dot, this is y equation. Okay. So x3 dot equation is, so x3 square minus x3 plus 3u2 equal to 0. So u is already 0. Okay, so now this would become x3 square minus x3 cube equal to 0. So this is second. Okay, so now in this what we can do, so we can take this x3 out. Okay, it will become what? You take x3 out, x3 square, it will become 1 minus x3. Correct? So it means that you'll have two things. So either x3 is 0, okay, x3 square is 0, that means x3 is 0, okay, or the second one is 1 minus x3 equal to 0, x3 becomes 1. Okay, now solving equations one by one. So what do we have here? So we are getting two things, x3 is 0 and x3 is 1. Okay, let's start with x3 as 0. Okay, first case. Okay, so when you take x3 as 0, so you can see here, so from here, okay, so we can calculate x2 first. Okay, so what is x2? X2 also becomes 0 from this equation. Okay, when x2 is 0 from this equation, x1 becomes infinity. X1 becomes infinity. Okay, so this is not possible. Why? Because states never becomes infinity. Okay, so that is for the first case. Okay, so when you see the second case, okay, x2, this case, x3 equal to 1, okay, in that case, okay, so you will get from this equation x2 and x2 same. Okay, so that means x1 is equal to x2. Okay, so that is first. Then using this condition, okay, you will get x1 square equal to 1. It means that x1 is equivalent to plus or minus 1. Okay, so now the overview. Now the overview. So we call this as equilibrium point. The point when we make x dot equal to 0. Okay, so we have two combinations. Two combinations. Okay, so first one is uh, x3 cases we are not considering. So in both the cases, x3 is 0 we are not considering. We are considering only x3 equal to 1. Okay, so in both the cases that is 1 1. Okay, so whereas here x1 having two options. Okay, so 1 minus 1, another is plus 1. Okay, second, so similar way you'll get x2 as two values. Because based upon the x1 you'll have x2 as two values. Now you see these are the equilibrium points. So these are what equilibrium points. Is this clear? Any doubt here till this point? Any doubt or query? Finding equilibrium points. Any doubt? Any doubt or query? Okay. So now we are going to linearize the system with respect to these 2 points. Okay, linearize the system. Okay. Okay. So first one is, so we have to find the ABCD matrices with respect to those 2 points. Okay. So first one is A matrix. What do we do is we have total here uh, three functions, F1, F2, F3. Okay. So we first write them. So A matrix is going to be dou F1 by dou X1, dou F1 by dou X2, dou F1 by dou X3. Okay, so this is first one. Second one is dou F2 by dou X1, dou F2 by dou X2, dou F2 by dou X3. This is second. Third one is dou F3 by dou X1, dou F3 by dou X2, dou F3 by dou X3. So this is called as the Jacobian. Okay. So now we are interested to find this. Okay. So given F1, F2 and F3. Okay. So similarly, let's write down the B also, then we will calculate. Okay. So the B matrix, is, so dou F1 by dou U1, dou F1 by dou U2. Why? Because why we are taking U1, U2? Here our system equations has U1, U2 terms. Okay, so that is the reason. Then dou F2 by dou U1, dou F2 by dou U2, dou F3 by dou U1, dou F3 by dou U2. Okay, so this is another way. Okay, so the third one, C matrix. Okay, so that will be like, so here this one is dou F by dou Xi. This is dou F by dou Ui. This is going to be dou Z by dou Xi. Okay, similarly D will be nothing but dou Z by dou Ui. Okay, that is how we will do the calculations. Okay, then C here is dou Z by dou X1. Okay, dou Z by dou X2, dou Z by dou X3. Okay, next last one is dou Z by dou U1, dou Z by dou U2. Okay, is this clear? Any doubt? Any query here? This is how we will do the calculations for finding the ABCD matrices. Okay, so first we will find these matrices, then we have to substitute these two vectors in the matrices so that we'll get a different set of ABCD matrices. Okay, first let us see what do we have here. So for F1, F2, F3, F1 is minus X1, X2. Okay, so F1 is minus X1, X2. Let me write somewhere so that it will be easy for us to do the calculations. Let me write here. F1 is minus X1, X2 plus 1. So F2 is X1, X3 minus X2 plus U1 plus U2 square. Okay, let me write that. So X1, X3 x3 minus x2 plus u1 plus u2 square. Then f3 is x3 whole 1 minus x3 plus 3u2. Okay, so that is x3 square into 1 minus x3 plus 3u2. Okay, then finally g is nothing but this one, last one. Okay, so that is x1 square plus x2 plus x3 plus u. Okay, so these are the functions. Now directly substitute these to get the expressions. Okay, let's check one by one. Okay, so first one is dou f by dou x1, that will become minus x2. Okay, next dou f by dou x1, so that is minus x1. Dou f1 by x3 0. Then x3 f2 expression with respect to x1 is x3, with respect to x2 is minus 1, with respect to x3 is x1. Okay, last one is f3, this expression. Okay, with respect to x1 is 0, x2 is 0, x3 is 2x3 minus 3x3 square. I think it is correct. Okay, next. Okay, so this expression is with respect to the u, all x will become constants there. Okay, so first equation with respect to u0, with respect to u2 0. Then this will become 1 to u2, last one is 0, 3. Okay, next. So this one with respect to x1, last equation. Okay, x1 is 2x1, next is 1, next is 1. Last equation with respect to u. Okay, so this is u1. Okay, so what does it become with respect to u1 is 1, u2 is 0. Okay, so these are general expressions. These are general expressions. So I think this should be clear. Any doubts? Okay, so now what we need to do is let's call this as x equivalent to uh, equilibrium 1, equilibrium 2. Equilibrium 1 is 1, 1, 1, 2 is minus 1, minus 1, 1. So you have to substitute them here. Okay, so let me write them again. So equilibrium 1 is how much? 1, 1, 1. So that is 1, 1, 1. So equilibrium 2 is so minus 1, minus 1, 1. Okay, you need to substitute both and get the two matrices for each case. Okay, so each case you will get 3 by 3 matrix here, here, and here also you will get two matrices. Here also you will get two more matrices. Okay, here also you will get two more matrices. Okay, so I'll just to give you the values, you can check them later. Okay, so first one you will get 1, 1, 0. So 1 minus 1 minus 1, just you need to substitute to uh, this vector in this vector. Okay, so 0, 0, minus 1. Okay, so this is with equilibrium 1. With equilibrium 2 you will get, with equilibrium 1 you will get the other matrices as 0, 0, 1, 0, 0, 3. Okay, the last one is you will get 2, 1, 1, and here you will get 1, 0. Okay, So that is with respect to the uh, equilibrium 1. Okay, so equilibrium 1. Next, with respect to the equilibrium 2, you will get 1, 1, 0, 1, minus 1, minus 1, 0, 0, minus 1. Simply in this, these equations, these matrices, you have to substitute the second equilibrium point. Here you'll get them as 0, 0, 1, 0, 0, 3, and the next one as minus 2, 1, 1, last one as 1, 0. These are the matrices. Okay, so that is our question. The question is to find the find the equilibrium point. Equilibrium points are nothing but these 2 points. Okay, so one equilibrium point is 1, 1, 1. Second equilibrium point is minus 1, minus 1, 1. That is first one. Linearize about the equilibrium point. With respect to these equilibrium points, okay, so using the Taylor series expansion. So if you use the Taylor series expansion, so these are the matrix expressions we will get. 4 matrix expressions. Okay, so that is called as the linearization. So linearization with respect to the equilibrium point. So both of equilibrium point you will get different set of matrices. Okay, so these are the matrices A, B, C, D for this linearized system of equations. Okay, so any queries here anywhere? If you have any queries, please ask. If you're having any queries, please ask.
No, sir.
Yeah. I mean, any doubt here finding equilibrium point practically? So what you need to do is you take the x dot is equal to 0 given equations. Okay. So the given equations are nonlinear system of equations. These equations take x dot is equal to 0. Solve for the equations. You will get different sets of x1, x2, x3, x4. Okay. So
Yes.
then these are the expressions, Jacobian expressions. Okay. So for finding the ABCD matrices, so once you know the functions f and z, so these are the matrices you will get. Then substitute those equilibrium points. So around that equilibrium point, these are the matrices. Okay. Yeah. Any other queries?
Where we use the Taylor series?
A Taylor series. Yeah. Here. So Taylor series we will use to get these matrices. I'll tell you how. So as I said, equilibrium point, correct? So equilibrium points in the sense, what we do is, uh, so in the Taylor series, so suppose here we are saying that we wanted to linearize. Okay, so we wanted to linearize the system, okay, given system of equations. Let's say about some equilibrium point x equivalent y equivalent. Okay, so so basically what we do here is with respect to that equilibrium point, okay, let us say this is the equilibrium point. Okay, with respect to that equilibrium point, what we do is we give some small disturbance there. Let's say that disturbance is dou x equivalent to uh, x minus x equivalent. That's that much disturbance we are giving. Okay, Then similarly dou y equivalent to, let's say, it's not in the y, in the input u minus u equivalent. Okay, it means that here the equilibrium also has u. It is something like this. Okay, so is my point is clear? You have x and u at this particular point. Okay, so the linearization says that from this particular point, if you give this small disturbance, something like this within this small region. Okay, so this is the disturbance. Okay, so equilibrium point is something that again your system will get back to the equilibrium point. That's the intention. So this one says that x equal to delta x plus x equivalent, and this one is u equivalent to delta u plus u equivalent. Clear? So now the Taylor series, we know that. Okay, so Taylor series, how could you write? So for this delta x, okay. So in general, what is the Taylor series? How do we write in general? So in general, we write the Taylor series as let's say f x comma u. Okay. So or else in general, we write f of x as, so f of x naught, okay, plus dou f df by okay, so dx, correct, delta x, okay, plus what is the next term, d square f by dx square, okay, delta x whole square, etc., all higher order terms. Is this clear? Yes or no? Okay, so let's say in our case, how can we write? So we could write x dot as, okay, so f of x comma u. That how could I write in the Taylor series? You'll have f of x equivalent u equivalent, okay, plus dou f by dou x. Okay, so with respect to the x equivalent, u equivalent multiply del x plus dou f by dou u. Okay, dou f by dou x only. Okay, so that is with respect to the x equivalent, u equivalent multiply du. So etc., you'll have higher order terms. Is this clear? So this is what we are writing. X dot is equal to f of x comma u. That is our function. Okay, so with respect to this equilibrium point, x u u u equivalent, this is how we will write. Okay, so from this we will get these matrices terms. Am I clear?
Yes, sir.
Yeah, from those. Okay, so you should remember these abcd matrices terms. Directly you can calculate the matrices. That's the intention here. Okay, yeah, next question. uh, Here the question is given as x dot is equal to ax plus bu, y is equal to cx plus du is given. So A, B, C, D matrices are given to us. Okay, so you have to find the transfer function, first one, right? After finding the transfer function, okay, so can we find this first order state space model, okay, of this form? Okay, so we are going and coming back in the reverse. Okay, so let's do that. Okay, so first one, what is the question? You have to find the transfer function. What is the transfer function? Y of s by u of S. Okay. So what is it generally? I think you have seen in the previous week that that is given as Si minus A whole inverse multiplied B plus D. That is the transfer function. Do you have any idea how it has come? Any any idea how it has come?
That eigenvalues we do na.
No, no, no. Directly you can consider these two equations, apply Laplace transform. Okay.
Hmm.
Find the expression for y of s by u of s.
Yes.
Okay, so you will get this. Okay, now our first question is to find this expression. Okay, so what do I do? So we'll start slowly one by one. Si minus a first. Okay, so si. So s0 0 s minus a is 3 2 3 4. Okay, so that is s minus 3 minus 2. So this is minus 3 s minus 4. Okay, next we find the inverse. Si minus a whole inverse is, so you'll find the det, that is s square minus 7s plus 12 first terms minus 6 second term. So what do we do? S minus 4, s minus 3, 2 and 3. Hope this is clear. Okay, so if you simplify it, you will be getting that as, so here you will get s plus 6. Okay, so that can be written as s minus 6, s minus 1. And this one has s minus 4, s minus 3, 2 and 3. This is your transfer function T of s. Okay, so that is first term. The next term is what? So you have to take, no, sorry, this is not the transfer function. This is Si minus A whole inverse. So the transfer function is C multiplied Si minus A whole inverse multiplied B plus D. Okay, so we could write that as C is 1 0. Okay, Si minus A whole inverse is this term, that is 1 by S minus 6, S minus 1, S minus 4, S minus 3, 2, 3. Okay, and last one is B. Okay, so what is B multiplied 1 comma 1 plus 0. D is 0. Okay, so if you simplify that, everything you will get 1 by S minus 1. So please check these calculations. You'll get 1 by S minus 1. That is our first question. Okay, is there any doubt in this? Any doubt in this? No. Okay. Yeah. Second question, from the transfer function, so we have to find the alternate first order state space model. What is the transfer function here? 1 by S minus 1. Okay. So transfer function is y of s by u of s. Okay. So that is 1 by s minus 1. So we are solving the second question. This is first question. Okay, so from here what do we write? S minus 1 y of s equal to u of s. Okay, so this can be written as s y of s minus y of s equal to u of s. So if you take the inverse Laplace transform, take the inverse Laplace transform. Okay, so what do we get here? This you get as y dot, second term is y, third term is u. Okay, is this clear? Any doubt? Any doubt here?
No, sir.
No. Okay, so this is your equation now after applying the inverse Laplace transform. So now let us consider x as the state variable. X as the state variable. Okay, so now let us take let x equal to y. Okay, so what does that becomes? X dot is equal to y dot. What does that becomes? So x dot is equal to y dot means what? Y plus u from here. Y dot is nothing but y plus u. Okay, so that is first equation. X dot is equal to x plus u. Why? Because x is equal to y. Okay, so now what is the state space model? What is the state space model? X dot is equal to x plus u, y is equal to x. Okay, so this is nothing but we have to put it into this format. Okay, that is nothing but x dot is equal to ax plus du, y is equal to cx plus du. Okay, so where a equal to 1, b equal to 1, c equal to 1, and d equal to 0. So that is how we will find the state space model from the transfer function. So this is an example of finding state space model from transfer function. Okay, whereas this one is what? From state space to transfer function. Okay, so the second question is from transfer function to state space. This is state space to transfer function. So what is the main observation here? Can you tell me? What is the main observation?
No idea, sir.
Here the main observation is what we are doing basically. We have started this state space, okay,
Yeah.
found the transfer function, okay.
Yes.
Then second question we started with the transfer function and end up with the state space, correct? Now what is the observation? Here look at these ABCD matrices. We started with these ABCD matrices, found the transfer function, correct? Then second question, we started with the transfer function. We are trying to finding the ABCD matrices. Okay, are they same? No,
No, they are not safe.
they are not same. Okay, so generally what do we expect? We expect that because we are doing the same problem, so we are doing conversion from one thing to other and we are going back. Okay, so we expect that we should get same, but we are not getting same. Okay, the reason is that so the state space representation may not be same for a transfer function. It may have different. Okay, so that's the conclusion here from this problem. Is this clear? State space representation may not be unique. The matrices may be different. Okay, yeah, so basically here the A matrix, here it is 2 by 2, correct? But here what we are getting is order is 1. It means that so the one more order we are losing in these calculations. Okay, actually here we are supposed to get 2, but here we are losing one order. So that's why only order is 1 here. Is this clear?
Yes, sir.
Yeah, yeah.
Sir, how
So
is order 2, sir?
yes, yes. What is the question?
How is the order 2?
No, no. Here, see, generally A matrix is 2, no? 2 by 2.
Yes, sir.
So if you do for any transfer function, you'll get order 2. Okay, in general.
Okay, sir.
Okay, but here the pole zero cancellation is happening in these calculations. That's why we
Oh,
end up with the order 1.
okay.
Okay. Yeah, so that is the one reason. So then when we are going from this transfer function to this state space, we are not getting the same matrices AB. Yeah, same given matrices. Okay.
Yes, sir.
This means that for a given system, state space representation is not unique. You can have different. Okay.
Okay, sir.
Yeah. If you're having any doubts, please ask me. So we'll have a small break of 5 minutes and then we'll continue the problems.
Yes, sir.
Yeah, yeah. Just 3 minutes break and then we'll continue. Okay. Welcome back. Can you hear my voice? Hello. Can you hear my voice? Is my voice is audible? Hi. Okay. Yeah. Thanks. Okay. So now look at this question. Okay. So the question says that given this system of the system described by this equations. Okay. So from this we have to find the uh, state space system. Okay. Now first what I'll do is, so I'll start with the basic one without this term. Okay. So let's start with that. So assume this is the problem given. Okay. So dt cube plus 3d square y plus dt square plus 2 dy by dt plus 5y equal to 3u. Okay. Here intentionally I'm not including that term. Okay. First we wanted to go step by step. So this 7 du by dt we will add later in the next step. Okay. So first we assume that we are solving this problem as an example. Okay. So first what we do is, first we choose the number of state variables. Number of state variables as 3. Okay. So that is equivalent to order of the system, order of the differential equations. Okay. So then, so we can choose them as x1, x2, x3. Okay. So let's start with the x1 of t as y1 of t. Okay. So x1 of t as y1 of t, let. Okay. And we choose the second as, okay, so that will be dx1 of t by dt, dx1 of t by dt, which is nothing but what, d so sorry, this should be y of t. Okay. So dy of t by dt. Okay. So the third state variable as, okay, d square x2 of t by dt square. That means what, d uh, d square y of t by dt square. Okay. So this is how we will proceed in the increasing order of magnitude. Okay. So first we will go ahead. So what is x1 of t dot, that is y of t dot. What is x2 of t dot? So that is nothing but d square, correct? So that is y double dot. Okay. So y double dot is nothing but what? So that is y double dot. Okay. Next. Okay. So what is x3 of t? Okay. x3 of t is nothing but what? So that is mm, d square, that is d, sorry, y triple dot, correct? So now from these equations, what is y triple dot is, we can write it. Okay. What is that exactly? So we can write one by one. Okay. So what is it basically? From these equations, you can write this one as, so 3u minus 5y minus 2 dy by dt minus 3d square y by dt square. correct, from this equation 1. Okay, so now you can see these three equations we have. Right side, left side is x1 dot, x2 dot, x3 dot. Fine, there is no issue. Left side, what do we have? Left side, y1, y dot. What is this y dot is? X2. Okay, what is this y double dot is? X3. Okay, so what is this one is 3? I can write that one as minus 5x1, correct? Minus 2x2 minus 3x3, okay, plus 3u. Is this clear? Any doubts? Any doubt in these equations?
No, sir.
Simply given system of equations, how we are writing the state space form. That is the intention. Okay, so now look at these equations. So these three equations, how can we put them in the matrix form? So x1 dot, x2 dot, x3 dot. Okay, so this would be like x1, x2, x3. Okay, so plus we have single input u. Okay, can you tell me the matrices? So can you tell us the matrices? The first one is,
Sir,
yeah,
sir, have you left in the equation that 7 du by dt on the left
yeah,
side?
yeah. I have started with without that.
Oh, okay,
Yes, yes. We have not entered into that problem yet.
okay,
Okay, so I'm just explaining first because that is the special case. Adding derivative of the input is special case. Okay,
okay.
you will see that why I
Ah,
left intentionally. Okay,
okay.
so
Let's
now
see.
you could see what is this matrix is. This matrix is 0, 1, 0. Why? Because I need to get x2 here. That's why I kept 1 here. Clear? Then second one is 0, 0, 1 because I need to get only x3 here. Okay, here this will be 0, 0. Third one is what? Minus 5, minus 2, minus 3, plus 3. Is this clear? Please check this method once. Please check this method. If you are having any doubts, please ask me. Then we will enter into the main given problem with considering the 7 du by dt. Is there any doubt? When a differential equation is given, to convert that into state space equation, what we do is we start with this first base here. The order is 3. Okay, number of state variables equivalent to 3. So we are choosing x1, x2, x3. Okay, so the first one will be y. The second one is derivative of the first one. Okay, the third one is derivative of the second one. So this is the first term in this equation. Oh, sorry. So then we
So
are
that would
taking
be
the
d cube, no?
no, here
D
you could
cube.
see. Here you see. So we are taking the first derivative x1 dot y dot is equivalent to x2 from here. Clear?
Yes.
Then x2 dot y double dot that is equivalent to x3 from here. Okay. Then x3 dot y triple dot that we take from the problem.
Oh, that are two cases. Okay.
No. Y triple dot from the problem, that is nothing but what? This whole part we take this side. That is our y triple dot. That's what we are doing. Is this clear?
Huh.
So all these terms we know. So we are
Y triple
substituting
dot
here.
means y triple dot means three time derivation that d to the power
Yes, yes,
cube.
Yes,
So
exactly.
in the left side, we should write na d cube of yt upon dt cube.
This one only, no? Y triple dot is nothing but this one only.
Huh, yes. On the left side, just I'm asking x3t where what we have
Yeah,
written.
x3 dot.
Oh,
What,
x3
what
dot.
is that equation?
Okay,
What is our
okay,
system
okay.
of
X3 dot.
equations? Our system of equations are first derivative only. Okay.
Yes, yes, yes. Fine. Fine.
Now, now, so now let us consider this problem, given problem. Okay, so intentionally I have left that 7 du by dt. Okay, now if we include that also, okay, so basically what we are doing here, we have three state variables. We are choosing x1, x2, x3 and x1, x2, x3. So we are starting with y du by dt, d square u by dt square, then derivating them. Okay. So now what if we include this one also? What is the major change I'll be getting? Can you tell me? If I include the given derivative of input also. If I include derivative of input also, what is the major change?
Will we get one more state, sir?
No, no, states are same. States are equivalent to always equivalent to this one.
Okay.
I'm not changing that. That will be 3 only. Number of states is equivalent to order of differential equation. Highest order. Okay. See here, this side, you could see here, what do we have here? X2. What do we have here? X3. What do we have here? X1, X2, X3, U. Correct? So that's why this side we got A matrix, X matrix, B matrix, and U matrix. Correct? So while choosing these terms, we have to be careful. Okay, so I'll tell you how. Okay, so let's start with that. So the given problem is d square, sorry, d cube y by dt cube plus 3d square y by dt square plus 2 dy by dt plus 5y equal to 3u plus 7 du by dt. Okay, so let's bring this one this side. So what do we have? D cube y by dt cube minus 7 du by dt equal to minus 3 d square y by dt square minus 2 du by dt minus 5y plus 3u. Is this clear? Now what I would say is this equation and this equation both are same. Okay, that is my claim. Okay, is this clear? That is my claim. So what I'll do is now, so I'll start choosing the variables, 3 state variables only. So first one is x1 of t, that is y of t only. There is no change. Okay, second one is x2 of t. What I wanted to do is I wanted to take like this. Okay, so third one is that makes choosing third one makes the difference. So previously what we have chosen for the third one, this one, correct?
X3 na?
X3 d square y by dt square, correct?
Hmm. Hmm. Yeah.
Now tell me what should I choose here? Previously that this term is not there. Now we are including that term also. So
Yes.
previously what I want here, I want this term only, correct?
Hmm. Yes, sir.
So I've chosen my x3 as what? One order below that, correct?
Yes, sir.
Now what I want my x3 dot should be what? I want my x3 dot should be this one. Okay.
Uh-huh.
What should I choose now here? Tell me.
Okay, so we will
Minus
d
7
square
u.
by upon dt square minus 7.
This is what I choose.
Okay.
What does it mean? If I take the differentiation, I'll be getting this, correct?
Hmm.
So let's take the differentiation. X1 dot, what is it? Y dot. X2 dot, what is it? Y double dot, correct? X3 dot, what is it? Y triple dot minus 7 U dot, correct? X1 dot is Y dot, am I correct? Yes or no? Yes or no?
Yeah, yes, sir. Yes, sir.
So X2 dot is this. X2 is this. X2 dot is derivative of that, Y double dot. X3 dot is this. Derivative is nothing but what? Y triple dot minus 7 U dot. Okay. So basically what is this one is? What is this one is? Minus 3. This one only, no? Minus 3 Y double dot minus 2 Y dot minus 5 plus 3U. Am I correct?
Yes, sir.
So what is this one? This is going to be what? X2. Am I correct? Y dot is nothing but what? X2. Correct?
Yes, sir.
Okay. Now, Y double dot is nothing but what? From this equation. X3 plus 7U. Sorry. X3 plus 7U. Correct? Yes or no? What is the last one? Minus 3. Y double dot is nothing but what? X3 plus 7U. Correct? Yes or no? From this equation.
Y double dot is x3 minus 7.
X3 plus 7U. This has to go this side.
Y double dot.
Yeah, Y
Oh,
double dot only.
oh, okay, sir. Okay.
Okay.
Yes, sir.
Now minus 2 Y dot is nothing but what? X2 minus 5 Y is nothing but what? X1 plus 3U. Is this clear? Is this clear now?
Yes, sir. It's clear now.
So now we have the equations. X1 dot equal to X2. X2 dot is equivalent to X3 plus 7U. X3 dot is equivalent to minus 5x1 minus 2x2 minus 3x3. What is last one? Minus 21 plus 3 minus 18u. Is this clear? Okay, so what is the format now? Plus this is u of t. So x1 dot, x2 dot, x3 dot. Okay, so x1, x2, x3. Okay, so first equation is 0, 1, 0. If you multiply it, you'll get x2. Is this clear? So this one is 0, 0, 1, 7. This is 0. Okay, the last one is -5, -2, -3, 18. Is this clear now? Check once.
Yes, sir.
Okay, so what is the key point here? So whenever you have the derivative terms of the input also included. Okay, so this is the key point. Choosing x3 is important. Okay, so previously, whenever we don't have this in the equation, we have only 3u. So I have directly chosen this x3 as d square y by dt square, correct? If that 7 du by dt is not there, this is the case. Is that clear? When I have included that also, so I have included that 7 ut as extra term. So that if I take the derivative, it will become 7 du by dt. Is this clear?
Yes, sir.
So this is the significance of this problem. Adding the derivative terms in the input, how do we convert given differential equation into the state space system? Okay. Clear? So after that, finding y is same. What is this from this equation we have? Y is equal to x1, correct? What is that equation? How can I write this one? I can write this one as 1, 0, 0, x1, x2, x3. Am I correct? Yes.
Yes, sir.
So this is your A matrix, B matrix, C matrix, and D matrix is 0. So that is 0 matrix. This is C matrix. Okay.
Yes, sir.
Okay. Any queries? Okay. So this is same problem. Same problem. Okay. You can also solve in other way. So the other way is like, so this is the problem given. So d cube y by dt cube plus 3 d square y by dt square plus 2 dy by dt plus 5y equal to 3u plus 7 du by dt. Okay, suppose now tell me, if I have some 8d square u by dt square, so what should I do? What should I do? Can you tell me?
For what, sir?
Suppose one more term is there here in the problem.
Like d cube u upon dt cube.
Yes, yes, yes. Like I've added extra term here. Okay. Still my number of state variables are 3 only.
Yes.
So what should I do now? So here one more term will come. minus
One
8
more term will come at x3. Huh.
du by
Yeah.
dt. Okay,
Yeah,
but
yeah, yeah.
entire calculations will be different. Okay,
Oh, yes.
so but that is how you will find. Okay, so that is one approach.
One term will add
Yeah,
in
one term will be added.
with
So
with
one more
x3.
other approach is for these kind of problems. Okay, so what do we do? This is the given problem. This is the given problem. So what do we do here is, so the approach, I'll not solve the entire problem, but I'll give you the idea. So x1 dot, you'll be choosing x1 dot as previously it is y. Now you will choose y minus alpha 1 u. Okay, x2 as x1 dot. Previously you have chosen x2 as x1 dot only, but now you will add this term also. And x3 as x2 dot minus, previously I have chosen till x2 dot only. Now you are adding this term also. So these are the basic state variables you will choose. Okay, where alpha I they belongs to R. Okay, so where here alpha i's are 1 2 3, they are called as the free constants. Free constants, is this clear? So then what we do is, you will take x1 dot. What is x1 dot? Y dot minus alpha 1 u dot. Am I correct? Okay, so what is y dot is?
Yes, sir.
Okay, so what
So
is,
our y dot is our x1 dot. Huh.
sorry.
Nothing.
Yeah, so what you can do is, from this we'll try to find the x1 dot in the reverse way. So from here, what do you write? X1 dot is what? X2 plus
X2 plus
alpha 2
alpha
u,
du.
correct?
Hmm.
Similarly,
Yes, sir.
from this way, you can write x2 dot. What is it? x3 plus
Uh,
alpha
alpha 3
3u,
u.
correct? Yeah. So similarly, you will start finding what is x3. What is x3? What is x3? We can write x2 dot minus
Minus
alpha
alpha 3 u.
3u. Okay. What is x2 dot? Directly from here. x1
x3
double
plus.
dot. No, from here.
Uh,
x1 double dot minus alpha u dot. Correct? Minus alpha 3u. Am I correct? So what do we
huh.
get here? x1 double dot is nothing but what from here?
But 2 u dot, then
Y double dot minus alpha 1 u double dot. Correct? Yes or no? Minus
alpha
alpha
1
2
u
u
double
dot
dot minus alpha 2 u
minus
dot
alpha
minus
3
alpha
u.
3 of u. Huh.
Okay. So like this you will continue. Okay. So what is my x3 double dot now?
x3 double dot or
x3,
x3 dot?
yes, x3 dot, sorry.
Huh.
That will
So
be this
x3 dot
equation.
will be y
Y
triple
triple
dot
dot.
minus alpha 1 of u triple dot minus alpha 2 of u double dot.
Yes.
Then minus alpha 3 of u dot. Yeah.
Okay. So now you have these three equations.
Hmm.
Okay.
Now
Okay.
I got it.
So now in these three equations, you have different terms. Okay. So
Hmm.
substitute those terms. Okay. Now choose your alphas. Okay. In such a way that, here the problem has only up to u dot, correct? In such a way that u double dot comma u triple dot make it to 0. Is that clear? Because you don't need u double dot and u triple dot. Okay, so then write down these equations.
When my u double dot and u triple dot is equals to 0.
So you choose your alphas. Okay, any value, because I said that they are free constants. Okay, after writing these 1, 2, 3 equations, you choose your alphas in such a way that u dot and u triple dot do 0. So you will get these equations. Again, these 3 equations. Okay,
So
so
it
that
like
from
x3
these
dot
you will
will
write
become.
your AB matrices.
Hmm.
Okay, so that matrix
ABC.
will be same as this.
Hmm.
Okay, so try to do this as exercise.
Okay.
Okay, this is general problem. Otherwise, you have to choose it based upon how many times the u is differentiated. You have to take this term correspondingly. Okay,
Yes, sir.
yeah. Okay, I think you can find this transfer function similarly. It is same as that of previous one. Y of s by u of s equal to c si minus a whole inverse b plus t. Same thing. You can find this, not an issue. And we'll see this problem, last one. Okay, so what is this problem says? Given x dot is equal to ax plus bu, find out e power at, then solution to x of t. Okay, so first one is e power at. What is e power at? How do we find? That is L inverse of si minus a whole inverse. State transition matrix. Okay, so L inverse of si minus a, s0, 0, s. Any doubt in this formula? 0, 1, minus 1, minus 2. Okay, so this inverse, that is L inverse of, okay, so what is that equation? S minus 1, 1, s plus 2. Okay, inverse. That is L inverse of, what is the inverse? 1 by s square plus 2s plus 1, s plus 2, s plus 1, 1. Correct? Okay, so what is it now? So L inverse of, okay, so s plus 2 by s square plus 2s plus 1, 1 by s square plus 2s plus 1, 1 by s square. Oh, this should be minus, I guess. This should be minus. So minus by 2s plus 1, s by s square plus 2s plus 1. Is this clear? Any query?
No, sir.
Yeah. So now what we do is we apply the partial fractions inside these terms. L inverse of, so I'm writing it directly. First one becomes 1 by s plus 1 plus 1 by s plus 1 whole square. Okay. Second one is 1 by s plus 1 whole square. The other one is minus 1 by s plus 1 whole square. This one is 1 by s plus 1 minus 1 by s plus 1 whole square. Okay. So now if you apply the Laplace transform individually, okay, here this term e power minus t plus t e power minus t. Second one is t e power minus t. This one is minus t e power minus t. This one is e power minus t e power minus t. Is there any doubt in this? Any doubt in this? So that is our e power at, this expression. Is it clear? Okay, so that is the
Yes,
first
sir.
question. That is the first question. Second question is to find the solution x of t. To find the solution x of t. Okay, so how do we find? Let us see the expression. So we have to find the expression for x of t. So let me write it here. Okay, so we have x dot is equal to ax plus bu. Okay, so apply Laplace transform on both these sides. S x of s minus x of 0 is equal to a x of s plus b u of s. Correct? So from here, how do I write? If I take x of s common, so si minus a. So let me write this as x only. Okay. So this would become what? X of 0 plus b u of s. Okay. So this implies x of s. So this is a matrix. Okay. So when it goes that side, si minus whole inverse x of 0 plus si minus a whole inverse b u of s. Is this step clear? Okay. So take inverse Laplace now. Inverse Laplace on both these sides. Okay. So what do we get? Here this will be x of t. This will be L inverse of Si minus A whole inverse x of 0 plus second term is L inverse of Si minus A whole inverse B u of s. Am I correct? So this is nothing but x of 0. X of 0 is initial condition, constant. L inverse of Si minus A whole inverse plus so this one is L inverse of Si minus A whole inverse B u of s. B is a constant. Okay. So now can you see here? Basically, what is this one? This term is, what is this term?
E power 80.
Yes, exactly. So this is e power at, and here the B is a constant matrix. Okay, so I'm writing that one here. Okay, and here we are having two terms. Okay, so this is one term, this is one term. Let's say this is f of s, this is g of s. Okay, Laplace two s domain functions are multiplying in the s domain. What will happen in time domain? Two Laplace functions are multiplying. What will happen in time domain?
Convolution.
Convolution. So this will be x of 0 e power at plus b. Okay, so convolution of f of t star b of t. Sorry, f of t star z of t. Okay, so how can I write that? So e power at x of 0 plus, so convolution 0 integral 0 t e power a tau. Okay, e power a tau, because this is what? This is again e power at function only. Okay, so b u of t minus tau d tau. Okay, b also I'm sending inside. So finally, what is the function? X of t is equivalent to e power at. Okay, so x of 0 plus integral 0 to t e power a tau b u of t minus tau d tau. Okay, this is the final solution. Okay, so now in this we already know that this is our e power at expression. We already know this is our e power at expression.
Yes, sir.
So if you know the initial conditions, okay, so initial conditions are not given, so you can consider them as a 0. Okay, so then you can substitute into the equation. Okay, so you can take initial conditions as 0. So x of 0 is equal to 0. Okay, so then you can substitute. When you take initial condition 0, this term will become 0. Okay, and you will substitute e power at. Okay, so what is the solution? X of t is equivalent to integral 0 to t. So e power a tau b u of t minus tau d tau. So this is also equivalent to 0 to t e power a t minus tau b of tau d tau, because it is convolution. Convolution is uh, mutual side. Okay, so 0 to t. So we already have this expression e power at. So wherever there is a t, substitute t minus tau. Okay, so you will get what? T tau e power minus t minus tau. Okay, this is t minus tau. Okay, so plus, so also you will substitute b also. Substitute b expression. So I'm writing the final expression. You can check it, final solution. So what you do, you have already this e power at expression. Wherever there is a t, substitute t minus tau. That is first thing. Next, you can substitute. This is, sorry, substitute b, and u of tau is 1. Okay, if you substitute them, finally you will get what? 1 minus t e power minus t minus e power minus t e power minus t. This is what you'll get. Okay, so that is the final solution. This is for x1, this is for x2 state variables. Okay, so any query in this? Any queries? Yeah, so finally I'll give a rough idea for this problem also, then we will close. So here we have to, for the given circuit, so we have to consider two cases. Okay, in case 1, so we have to take VC1 comma VC2 as state variables. Okay, in case 2, we have to take VC2 comma VC3 as state variables. Okay, take all these values are ones. Okay, so then you have to find differential equations. You have to write the state space equations in both the cases. Okay, so you can apply the either KVL equations or KCL equations. Then you have to do some simplifications finally. So in first case, the equation should be like this: dVC1. Okay, so dVC1. Let me give you the answer so that it is easy for you to check. So you should be getting dVC1 by dt, dVC2 by dt. First case as minus 2 by 3 minus 1 by 3 minus 1 by 3 minus 2 by 3. So VC1, VC2 plus 2 by 3 1 by 3, and here it is V in here. Okay, that's first case. So second case, okay, in first case itself, you have voltage. So V naught equal to 0, 1, Vc3 plus 0, Vn. Okay, so in the second case, dVc2 by dt, dVc3 by dt equivalent to minus 1 by 3, 0, minus 1 by 3, minus 1. So Vc2, Vc3 plus 1 by 3, 1 by 3. So, okay. So V naught is 0, 1, Vc2, Vc3 plus 0, Vn. Okay, so that's what the answers you should get. Okay, so maybe I would suggest you to go for maybe KCL in first case, KVL in the next case to get the answers easily. But I mean, there were other way also it should work. Okay, so I think we are running out of time. Already we have crossed 15 minutes. Okay, so we'll stop here, continue in the next live session. So next live session, we're not going to discuss no more problems in state space. We will get in the pole placement and observer design. Okay, so we'll also discuss the controllability and observability problems. Okay, so any queries? Okay, if there are no queries, we'll stop here and continue in the next live session. Thank you. Thanks a lot.
Thank you, sir.